One thing that is required in this course is to do to analyze the running time of one of these programs using what's called the master theorem. And you took 1019, in which you did some recurrence relations. And what I complained to the coordinator is that the course got us to do recurrence relations which don't come up in our regular in computer science. But we should instead do these ones, but we didn't. So now we're going to do these ones. All right. And what are they? So here's a typical recursive program. All right. And I mean, I just right now been marking some old third-year algorithms tests since they wrote them late. And it's amazing how many people still can't just get the right format for a recursive program. All right. So let's just kind of look at this. I'm given some input to my problem, and let n just denote the size of it. All right. And then if my input is so small that I can't make it smaller, and I can just sort of brute force it, right? If the input's only of size 0 or 1, then I can figure out what the answer is, right? And so I just give the answer and go home, right? Otherwise, I might do some work myself, in which case, you know, right? What my goal is to take my input, and I can have as many friends as I want, right? And you want to trust your friends. You don't want to micromanage your friends, right? You can give them any input that meets the precondition and that's in some way smaller, all right? And then you trust your friend to give you the answer back. So here, I have A friends, right? A some parameter, and I give each friend an input that, in this case, is my input's of size n, and my friend's input is of size n over b, right? So it's a b the size, right? And then I also do some personal work, right? I have to take my input and form the inputs for my friends, right? And I have to take my friends' answers and combine them to get my answer, all right? So here we're saying my work is some function f of n. Right? Everybody understand what's here? So all right, so here's the recurrence relation. All right, let's go through it again. So we're asking, we define P of n to be the amount of work for me and all my friends to solve a problem of size n. All right, so n is the size of my input. P of n is going to, in this case, is going to be the number of highs that get printed on an input of size n, right? And by all my friends, right? P of n is the work I do plus all the work my friends do and their friends and their friends, right? So suppose n is 1, then I print out 1 high. Now, as a general rule, we're kind of going to say that P of 1 is 1, right? Because we're doing big O notation. So even if my input is small and the base case has size 5, right, that's O of 1. And even if the work on an input of size 5 is 100, that's still O of 1, right? So that first line basically says, if you give me a base case, that base case is going to be size order 1, constant size, and the work is going to be some constant work. All right? And then now we're trying to calculate the total work done by me and all my friends on input of size n. So I do f of n work, right? And I have a friends. So I want to know how much work each, narrow down one friend, and how much work does he do in all his friends, right? Well, his input is of size n over b. So how much work does he and all his friends do is the t of that, right? Does that make sense? You getting this recurrence relation? Should we talk about it some more? Got a question about it? Do you see here? Basically, this is the size, n is the size of my input. T of n is how much work everybody together is going to work on an input of size n, right? Then I have a friends. So the total work is what? Is a times the work each of my friend does, plus the work I personally do, right? So now look at this subroutine call right here. Let's calculate how much work that guy and all his friends do, right? Well, if his input is of size n over b, then the definition of t is that t of I is the time to do it, to solve a problem of size I, and we're giving him a problem of size n over b, so it's going to take him time t of n over b. Yeah? Should I draw? You guys are so enthusiastic. Should I draw a picture on the board? So this is me, and this is this is my first friend and all of his friends, right? And this is my second friend, and this is my third friend and all of their friends, right? So the number of friends I have is A. Then how big is my input? My input's the size n. My friend's input is the size n over b, right? We're trying to calculate P of n, which is the total work in this whole thing, right? So how much work is in this whole thing? Well, kind of by the definition of t, it's going to be n over b, P of n over b. How much work am I personally doing? I'm personally doing f of n work, right? So what's P of n? Well, it's A times T of n over b plus f of n. Does that help at all? Not really, eh? Good? All right, so one way to solve a recurrence relation, like if I wanted to solve x squared equals 16, one way to do it is I'd guess x equals 4, and I note that 4 squared equals 16. It satisfies the equation, so I'm happy, right? Of course, that requires divine inspiration with your guess. So here I'm trying to solve, this is the recurrence relation, right? I have A equals 4 friends. I cut each input in half. B is 4. F of n is just linear, right? So there's your equation, and we can guess a solution, and we plug it in, and we see that it works, right? So that is the solution, but we don't know how to guess. All right, so what we're going to do here now is we're going to quickly go through the derivation of what's called the master theorem of how to solve these recurrence relations, all right? But, if it flows into you and it makes your life better, then that's great. But even in we're not going to test you on the proof, right? You're going to need to know how to do it. All right, so here's kind of the picture I have here, right? I personally am doing in work. I want to know the total P of n of when the inputs of size n, right? So that's me, and those are my 4 friends, right? It's the picture we just drew on the board. People get this picture, right? And so we can kind of unwind it, right? What's this friend? Well, he's given an input of size n over 2. He has 4 friends with inputs of size n over 4, right? So we can keep unwinding it all the way down until we get a base case, right? And so we can fill out this chart, right? And in this chart, there's one of me, and then, right, see, I'm at the top, there's one of me, and then I have 4 friends, and each of my 4 friends has 4 friends, and each of his 4 friends has 4 friends. So you see the number of friends grows by a factor of 4 each time. So we have 4 to the I friends at level I, right? And how much work is each doing? Well, first of all, how big is their input? I have an input of size n, so my friend is n over 2, his friend is n over 4, n over 8, n over 16, right? So at the ith level, the work at the ith level is n over 2 to the I, right? Everybody good with that? And so, and then how much work are they doing? Well, in this case, f of n is just n. So if I am given an input of size n over 2 to the I, then the amount of work I do is n over 2 to the I, right? So here are the levels, and we want to add up the total work at each level, right? So the number of friends at level I is 4 to the I, right? And the work each of them does is n over 2 to the I. So there's the equation which tells you how much work is done at this level, right? More or less okay? And then at the bottom here, after log n levels, right, then the number of base cases is 4 to the log n, right? Because it's 4 to the I, we're at level log n. And so, oh, and the, right? Here's just a little math you can do. A to the log n if you don't understand it. Well, you can define, right, what's 2 to the log a, right, is by definition a, right? People with that, 2 to the log a is a. Right, why? Because what's the definition of log a? Is 2 to the what gives me a. So, all right. And then how do you do 2 to the x to the y, right? Here I have the number of 2's multiplied as x. And then I do that again, another x, and I repeat that y times, right? This is going to be 2 to the xy, right? So we can just bring that. And then we can go the other direction. Now we have 2 to the log n. And what's 2 to the log n? It's just n, right? So that gives us that 4 to the log n is the same as n to the log of 4 base 2, which is 2, right? So you get n squared. And why is this 1? Well, because the size of the input keeps getting down until the inputs are of size 1, right? So now we have to add up all of these works, right? We got the work at each layer, right? How do we total it? Well, one observation is that term right there, it changes by a constant factor, right? The 4 to the I goes up by a factor of 4, and the other one goes down by a factor of 2. And so the point is it's changing. In fact, everyone gets bigger by a factor of 2, right? And one thing, you probably know this sum already, right? 1 plus 2 plus 4 plus 8 plus 16, right? Keeps doubling. Then what's the sum size? Well, we did a quick adding thing, remember? It's dominated by the biggest term, right? It's kind of 2 times the biggest term, which we're going to just say it's dominated by the biggest term. All right, so this is, right, we did that sum. All right, so now there are all these terms, and we want to know which is the biggest. And the biggest is either going to be at the top or at the bottom. And at the top we have n, and at the bottom we have n squared. So it's going to get dominated by the n squared, right? So the answer is order n squared. People kind of follow that? Now we're going to just do it again, but for an arbitrary a, b, and we're going to change the f of n into the c. All right, so how big is the instance? Well, I have an input of size n, and then n over b, right? We keep dividing by b, so we get n over b to the I after I levels. Yeah? Enthusiasm? So then we say, well, can we figure out how many levels there are? Well, here's some sort of math. We have b to the h is n, right? We keep divided by b until we get to 1. So b to the h is n. So you take the log of both sides. What's the log of b to the h? I don't know if you remember, the h can come down, right? And then here we got log n. And then we want to solve for h, which h is the number of levels of recursion. So h is log n over log b, right? And which is, and kind of it's the same as h is the log of n base b, right? You know, there are different bases in your, and here, since we're dividing by b, it's sort of like doing it base b. All right? And then we can say how much work is in the stack frame. Well, it's f of whatever that is, right? And how many stack frames are there? Well, it goes up. I have a friends. They have a friends, right? So it goes up by a factor of a, right? So now we want to calculate how many base cases there are, right? So we went to level h. So the number of base cases is a to the h, right? And what is h? H is log n over log b. So then, just like before, we can bring the a up, turning it into a log, and we can bring the log n down, and you get that the number of base cases is into the log a over log b. All right? Yeah. H is when you hit the base cases. It's how many levels there are until you hit the base case. So do you understand that at the ith level, it's the size of the instance is n over b to the I, right? So we're going to keep going until we get that the size here is 1, right? Yeah, sure. But here, right, if I'm doing merge sort, I have my big input. I give half to one friend. I give a half to one friend again, right? Until the inputs of size 1. Yeah. Well, we're not doing merge sort here. It's a whole different thing. I had 4 friends, and I was doing in work. I don't know. It's a different recurrence relation. Right. All right. What's really exciting about this is that it's a polynomial, right? A is a constant and B is a constant. So it's into some constant. Now, if I had 2 friends and they had 2 friends and they had 2 friends, and so then the number of friends is growing exponentially. And if I give my friend an input that's just 1 smaller, I had an input size n and then n minus 1 and n minus 2 and n minus 3, then the height of the recursion would be n, right? And so the number of base cases would be 2 to the n, right? But here, because we're doing so much damage to the input, it's going down by a factor of b. The number of levels is not linear, but is logarithmic, right? Everybody sort of follow that? Logarithmic base b. And so the number of stack frames is growing up by a factor of a. So it's growing exponentially, but only a log depth. And the a and the b balance here to make it a polynomial. All right? So I recommend that you memorize this recurrence relation, that I have a friends and everybody's input is of size n over b. And you memorize that the number of base cases is n to the log a over log b. And why should you memorize it? Well, because it will be on the test in this course. And certainly if you take 3101 from me, it'll be on the test in 3101. What? Not all this crazy math, not all this proving. All right? Let me tell you what you need to know. You need to understand this recurrence relation, where T of n is the time on my input of size n, A is the number of friends, n over b is what I give to my friend, right? And then my work is into the c. And then you should know that the number of base cases is into the log a over log b. All right? And this is the proof, but if you don't want to remember the proof, that's fine, right? Then we have to calculate what's the total work. Well, at the top level, there's just me. There's one of me, and I do f of n work. And at the bottom, each base case is a constant amount of work, but there are this many base cases into the log a over log b, right? And so we want to say, what's the sum? Well, probably the sum is whichever one's bigger, right? So we go back here and we say, is one of these bigger? And if it's bigger, then that's the answer. If they're both the same size, then all the layers in between will be the same size, and the answer will be the value at that level, that's the same, times the number of levels, which is log n. All right, so let's do that again, right? Right, so here's a little table. What does it say? T of n is the time for me and all my friends to solve the problem on input of size n, right? A is what? A is the number of friends. B is what? How much I cut the input down by, right? I go from an input of size n to an input size of n over b, right? If instead you went from an input of size n to n minus 1, bad, right? Because then it's going to be exponential, right? What's f of n? It's the work I personally do, right? Let's assume if f of n is n to the c for some constant c, right? And then it says we can be a little slacker, right? Well, if it's not quite n over b, that's fine. If it's a little off by n over b, that's fine, right? Even if you add a whole bunch of weird things, that's fine. It's just that n minus 1 is bad, right? All of these are more or less n over b, right? All right. So let's go over to some examples now, right? So here's the recurrence relation we saw before. You ask, what's the work at the top level? Well, it's into the C, where C is, what's C? 1, right? Because it's into the 1 is into the C, right? So C is 1. How much work, how many base cases do we have, right? We calculate log A over log B, and we get 2, right? So the number of base cases. And then we say 2 log A over log B is bigger than C, right? The work at the top, right, is into the C. The work at the bottom is into the log A over log B. So you compare them. And if in this case, the log A over log B is bigger, so that is the answer, right? The running time is dominated by the number of base cases, which is n squared, right? Does that make sense? Right? Now, let's just say we change that 4 to a 3, right? So what's going to happen? I have 4 friends, and they have 4 friends, and they have 4 friends. If we decrease the number of friends from 4 to 3, does the total work go down by 25%? Right? You think it might. But look at this. I kill one of my friends off. No, this is going to be Game of Thrones, by the way, right? So we just reduced the work by a quarter. But then each of my friends kills off one of his friends, and each of his friends kills off one of their friends, right? It's a bloodbath, right? So now let's just redo the thing, right? Now it's log A over log B. In this case, I don't know how to calculate log 3 over log 2. So I do the calculator, and I get 1.58, right? And so then the running time is into the 1.58, right? And if we were doing 3101, this is giving you an algorithm for multiplying a little faster than n squared. All right? Everybody kind of get this? Now, let's change this. I'm just making it weird ones here, right? Now, let's increase my work to n squared, right? So the top level is n squared. But here, n squared is bigger than the number of base cases, right? Log A over log B is 1.58, and C is 2, which is bigger. So what's the answer here? Right? It's dominated by the top. Right? Now let's do a really weird one. Let's say for some weird reason, I just happen to do into the 1.58 work, right? Then the top, all the levels, every level is going to be into the 1.58, right? So the total work, right? All layers require that. So the sum is into the 1.58 log n. right? Does that make sense? Right. Let's do some weird logs, right? Can anybody calculate log of 27 divided by log of 9? Some easy thing in your head? Well, 3, good, right? Because you don't know which base, and you can change the base. It doesn't matter, right? So if we do base 3, then did you say 3? Actually, it's 3/2. All right? Because we got do base 3. Everybody good? Right. So on the test, I don't give you calculators, but I don't ask you to do hard